Hello guys, welcome back to my channel, and in this video we would like to overcome some extreme adversity when we are solving an integral problem, and you'll see what the adversity is in a short amount of time. So let's get started. So the problem we have to deal with is basically called I, and it's defined as integral from 0 to pi over 2 of natural log of natural log squared of sine theta divided by pi squared plus natural log squared of sine theta along with the natural log of cosine theta divided by tangent of theta d theta. So before going forward with any monkey substitution, I would like to take this tan on in the denominator and write it in the numerator in terms of its uh, reciprocal trigonometric uh, quantity. So doing that, we have integral from 0 to pi over 2 of natural log of ln squared of sine theta divided by pi squared plus ln squared of sine theta along with a ln cosine theta and a cotangent theta d theta. And now if you have been practicing derivatives a lot, you'll notice that natural log of sine theta has a derivative which is precisely cotangent of theta. So we would like to go ahead and do that substitution. So let x equal natural log of sine theta, and dx is, you can do this, cosine theta over sine theta d theta or cotangent theta d theta, which is exactly this part. So now we have integral from when theta is 0, sine of 0 is 0, so natural log of 0 will blow up to negative infinity. And for pi over 2, theta being pi over 2, sine of pi over 2 is 1, natural log of 1 is 0. Integral from minus infinity to 0 of natural log of x squared over pi squared plus x squared, because natural log squared of theta is natural log of theta the whole thing squared, so that's x squared. And then we'll have a dx. But how do we deal with this natural log of cosine theta? So notice that sine theta from this, taking the antilog of this, is basically e to the x. And we know that cosine theta is nothing but square root of 1 minus sine squared theta. So cosine theta in this case is going to be square root of 1 minus e to the x squared, so e to the 2x, like this. And that is all inside a natural log. So natural log of square root of 1 minus e to the 2x, and then this underlined part on top is just dx. Okay, but look here, we still have to integrate from negative infinity to infinity. We can convert this from positive infinity to negative infinity by doing this, not exactly a substitution, more like a sign change. So more like symmetry, you can say. So instead of x, I'm putting negative x, because I'm not changing, I'm not introducing a new variable. We won't call this a classic substitution, but what that will enable us to do is have positive infinity and 0 because of this change, and then x squared being invariant under this transformation will just be x squared over pi squared plus x squared. And here we'll have natural log of square root of 1 minus e to the negative 2x, right, because we changed x to negative x, and then dx will naturally get changed to negative dx, so negative up front dx. So I'm going to use this negative to correct the order of integration from 0 to infinity. I can write natural log of square root as, using log properties, is half times natural log of 1 minus e to the negative 2x times natural log of x squared over pi squared plus x squared dx. So far so good. Now what I want to do is, notice we have a quotient in the argument of this natural log, so we can use natural log properties actually, doesn't matter what base we have, to write this as natural log of the numerator minus natural log of the denominator. So essentially splitting the integrals, so if you have integral of this, we can split integrals like this. So finally we obtain two integrals by linearity. So half of integral from 0 to infinity of natural log of 1 minus e to the negative 2x times the natural log of the numerator x squared dx minus half of integral from 0 to infinity of natural log of 1 minus e to the negative 2x and the denominator with a natural log of pi squared plus x squared dx. So call this I1, and this, along with the negative, you call that to be I2. Okay, so can be expressed as I1 plus I2. So let's do I1 now on a fresh page. See you there. So as discussed, here is I1. Now what I'm going to do before actually doing anything is bring this power of the x squared down using log properties. So we have half times this 2 and integral from 0 to infinity of natural log of x times natural log of 1 minus e to the negative 2x dx. These cancel. Okay, so now notice this log is actually in the optimal form of natural log of 1 plus some other variable, say, I don't know, f. I'm not using x's because you'll get confused otherwise. And when we have natural logs in this form, we can definitely employ Taylor series. It's almost like the Taylor series is tailor made for this part. So when I do that, we have integral from 0 to infinity of sum from k equals 1 to infinity minus 1 to the k plus 1 over k times negative e to the negative 2x, everything to the kth power, times the natural log of x dx. So now what I'm going to do is I'm going to assume uniform and absolute conversions, interchange the sum and the integral, and then pull out a minus 1 to the k. So minus 1 to the k with this minus 1 to the k will cancel out. So we'll have minus 1 to the 1. So that's just a plain negative sum from k equals 1 to infinity of 1 over k times integral from 0 to infinity of natural log of x times e to the negative 2xk dx. And at this point I would like to do a quick substitution. So let u equal to 2kx such that dx, after rearranging this, is du divided by 2k. So when we do that, we have minus sum from k equals 1 to infinity of 1 over k times integral from 0 to infinity. Upper and lower bounds are unchanged. Natural log of u divided by 2k times e to the negative u, and dx is du over 2k. Now pull the 2k outside the integral. So we have minus sum from k equals 1 to infinity of 1 over 2 squared, and then we can actually split this up into two different integrals using log property on this natural log of a quotient. So first is integral from 0 to infinity of natural log of u times e to the negative u du minus, we'll have natural log of 2k but natural log of 2k does not depend on u, so we can take that out of the integral. We'll have integral from 0 to infinity of e to the negative u simply du. Okay, so what are we going to do now? So notice that this is simply gamma prime of 1, or the derivative of gamma at the argument equals 1. And we know that this is equal to the digamma of 1, which is nothing but negative Euler-Mascheroni constant. So we'll have minus sum from k equals 1 to infinity of 1 over 2k squared, and this is minus Euler-Mascheroni, this part. Here we have minus natural log of 2k. This is simply gamma of 1, which is nothing but 0 factorial, which is 1. So just ignore that. So now basically cancelling out all the negatives, we have sum from k equals 1 to infinity of, take the half outside, and the Euler-Mascheroni if you want, 1 over k squared, and then we have split this natural log up, natural log of 2 over 2 times sum from k equals 1 to infinity of 1 over k squared, plus 1 over 2 times sum from k equals 1 to infinity of natural log of k over k squared. So this k, sum from k equals 1 to infinity of 1 over k squared, is nothing but the Riemann zeta of 2, which has a definitive value of pi squared over 6. Along with this Euler-Mascheroni over 2, so we'll have Euler-Mascheroni times pi squared over 12. Same thing here, plus natural log of 2 times pi squared over 12, and this is just the derivative of the Riemann zeta function at argument equals 2. And you can check this if you want. So if you have your original Riemann zeta of 2, say for example, you know, let's have a general Riemann zeta, say k to the z. That's your general Riemann zeta. So what if you differentiate with respect to z? This will be k to the negative z power. So it will be like an exponential function. When you differentiate an exponential, you will have a natural log of this base, that's k, over the exponential as it is, as the derivative. So that's Riemann zeta prime of z, and then when you plug in z equals 2, you just obtain this. So it's indeed half of Riemann zeta prime of 2. So that turns out to be the value of I1. It's a handful, I know, but that's how the question was. So like we had I1, we have now I2 also, and there's a negative half in front. Yeah. So I'm going to use the same technique that we did for I1. So we're going to write this as a Taylor series. So we have minus 1, and then integral from 0 to infinity of sum from k equals 1 to infinity of minus 1 to the k plus 1 over k times negative e to the negative 2x raised to the kth power times natural log of pi squared plus x squared dx. Now assuming absolute and uniform convergence, interchange both of these things and take a minus 1 to the k outside. So this will cancel out with one of these, and then we'll have minus 1 to 1 first power, which is just a negative. So that negative and this negative will cancel out, just giving us a positive. So half and sum from k equals 1 to infinity of 1 over k, and then integral from 0 to infinity of e to the negative 2kx power times natural log of pi squared plus x squared dx. Now, even if we were to use substitutions, we would not be able to reduce this down to any known special functions like the gamma, the Riemann zeta, or any other function. I mean, for the previous one, we actually used the definition of the derivative of the gamma at argument equals 1. And unfortunately, we can't do that because the derivative of gamma just had natural log of a single variable, x or z or anything. Here we have a sum of squares in the argument of the natural log. So there is still one thing we can do before doing something crazy. That's use integration by parts. So in integration by parts, let this be integrated and naturally let this be differentiated. So we now have half and sum from k equals 1 to infinity, multiply by a negative and take another 2 down. So we have a 4, basically for the antiderivative of this, and bring another k down. So we are basically dividing by 2k all the coefficients apart from x for the antiderivative of this. So we have 1 over k squared and a negative 1 over 4 outside, and then e to the negative 2kx times this as it is, pi squared plus x squared, evaluated from 0 to infinity, minus integral from 0 to infinity of e to the negative 2kx times the derivative of this will be pi squared plus x squared, and then you multiply by 2x because of the chain rule, dx. Okay, so at infinity, natural log will go to infinity, the e will also go um, to infinity, but it will be in the denominator. So we basically have 0 times infinity. This will decay, right? It's a e to the negative x, basically. So 0 times infinity, you can write this as natural log of pi squared plus x squared, pi squared plus x squared, divided by e to the 2kx in the limit as x goes to infinity. But the exponential will grow faster than the natural log. That's why it will dominate the fraction, making this entire fraction go to 0. So at infinity, we have a 0. And at 0, this will go to 1. And this will just be natural log of pi squared. So finally, we just have minus minus plus. So 1/4 times sum from k equals 1 to infinity of natural log of pi squared over k squared. And then this minus minus plus 2 over 4 is half, sum from k equals 1 to infinity of 1 over k squared times integral from 0 to infinity of e to the negative 2kx times x over pi squared plus x squared. I'm just basically separating terms. I'll bracket this out nicely, dx. Okay, so now what I'm going to do is I'm going to simplify this slightly so we can bring the power down from the pi squared, making this a half natural log of pi, and we have sum from k equals 1 to infinity of 1 over k squared, which is just Riemann zeta of 2 or pi squared over 6. And I'm going to call this entire thing I naught. And we are going to do something really crazy now when we are evaluating I naught. So equation for I2 just becomes um, natural log of pi times pi squared over 12 plus I naught. Let's do I naught on a fresh page, and there will be a lot of unexpected adversity and unexpected genius. Let's get let's discuss this on a fresh page. See you there. Yeah, so, and I must confess, before doing this weird method that we're gonna do, I actually did not was unable to solve this. I stopped at I naught. I mean, I got everything until I naught, and then I just stopped. I didn't know what to do. So the answer is, whenever you have integral from indefinite bounds, usually of, usually I'm not, I'm not specifying it. I'll just comment generally. Uh, this is the case, not always. If you have integral of, say, natural log of 1 plus some variable of integration, some polynomial actually, some polynomial times natural log of 1 plus another polynomial integrated with respect to, say, f, if your function depends on f, then you use this method, whatever I'm going to apply now. Okay, so you know originally we had this for I2. What I did was I used one of the simpler natural logs, wrote it in the form of its Taylor series, and then used integration by parts to somehow simplify stuff. And now we obtain this I naught, because that other part, most of it hopefully cancelled out. So now we're going to look at what we're going to do with this. Okay, so I would like to make a really, really nice observation here. Um, this seems like a Laplace transform value. So let me just give you, before concluding or explaining what that observation actually leads us to do, I would like to say that our Laplace transform of a function of t basically was integral from 0 to infinity of e to the negative st times f of t dt, right? This t was the input variable that we had, and whatever output we got depended on s. So we had basically e to the negative input, which was t, multiplied with output, which was s. And this, if you want to generalize, can be defined as Laplace transform of f of t with respect to s, and s can be any constant. It can be anything. It can just even be this 2k, or even a natural log in itself, which does not depend on t. It can be any constant. So in general, if you have f of t, you can find the Laplace transform of this with respect to any variable, any constant a, as integral from 0 to infinity e to the negative input, which is t, times output, which can be seen here or here, a, f of t dt, and this will give you a function of a. So using the same logic, say if we have the Laplace transform of say cosine of t with respect to s, this will be integral from 0 to infinity e to the negative xt cosine t dt. This will evaluate to basically that the Laplace transform of cosine is x over s squared plus x squared, but instead of x now we have, instead of s actually, let me just write the normal Laplace transform of cosine t, the normal one, like when s was our output value. So this is basically t over um, sorry s over s squared plus 1, and this 1 depended on what was multiplied with the t. If there was a phi, then we had s squared plus phi squared, like that. But instead of s, now we have an x, so x squared over x squared plus 1. Now what if, instead of having an input variable t, we have input variable y, again with respect to x, but not y, let's say pi y. So we have integral from 0 to infinity e to the negative well, in this case we will just ignore the constant, because anyways the input variable is y, not pi y. So pi x times cosine of y pi dy this is going to be basically x over x squared plus pi squared. And that's exactly what we have here. So what I propose to do is actually introduce this Laplace transform integral. I propose to write this bracketed term in terms of this integral, that is with respect to y, and then evaluate stuff. And this idea of introducing an integral inside an integral seems kind of weird and misguided, because we have to evaluate an integral. Introducing another integral should make stuff complicated, but it was actually Friedrich Gauss that actually used this idea. So I can call this Gauss's genius idea, because this was the only way he could actually calculate this Gaussian integral. He basically put another, if you call this I, he took another I defined as negative integral from negative infinity to positive infinity, e to the minus y squared dy, and then multiplied these two together. So he had an integral inside an integral like this, e to the negative x squared plus y squared like this, dx dy. So he had a double integral like this, and then he used polar coordinates and calculated this. I have made a video on this, but this is the entire idea that we are going to implement for calculating this integral, which is otherwise impossible to calculate using other techniques. So let's do that. So as we discussed, let's set up an integral inside an integral, because see, it worked for Gauss, it will work for us. So we have e to the negative 2kx, and then this bracketed term can be represented as integral from 0 to infinity of e to the negative xy times cosine of pi times y dy, and then this outer integral had a dx on it. Okay, fair enough. You know what we can do? We can actually take this outside. Right? Rather take the e to the negative 2kx inside the double integral. So I just took the e to the negative 2kx inside the double integral like this. And if you're confused, I'd like to remind you this bracketed term was actually the Laplace transform of cosine of pi y with respect to x. So we just use the definition of the Laplace transform, and then we got this integral. Here we are defining that Laplace transform goes from some function of y, so small f of y, to some capital function f, which is depends on x basically. So now I'm going to assume uniform and absolute convergence, interchange these integrals. So instead of dy dx, we'll have dx dy. So half of sum from k equals 1 to infinity of 1 over k squared, integral from 0 to infinity, integral from 0 to infinity, e to the negative 2kx, e to the negative xy, cosine of pi y, dx dy. I'm going to group some terms in the exponent, like integral from 0 to infinity, integral from 0 to infinity, e to the negative x times 2k plus y, cosine of pi y, dx dy. Since it's an integral with respect to x, we just forget, like we treat the cosine of pi y as a constant. So we have half of sum from k equals 1 to infinity, but we'll have to multiply with the negative because we are bringing this factor down. So we have a 1 over k squared multiplied with 2k plus y like this, and we still have let's write the 2k plus y inside the integral. Taking it out will mean it's because there's y dependence. So writing it properly, we have integral from 0 to infinity of, well, the first integral has been executed. So it's just cosine of pi y that was unchanged divided by this um, factor of 2k plus y, and we still have e to the negative x times 2k plus y, but evaluated now from x equals 0 to x equals, I won't say equals infinity, x tends to infinity. It's always limit as x tends to infinity. So as x tends to infinity, this will make everything go to 0. And when x goes to 0, we'll have a 1. So minus and minus will become positive half, sum from k equals 1 to infinity of 1 over k squared, and integral from 0 to infinity cosine of pi y over 2k plus y dy. Fine, we got rid of our double integrals. If you're feeling kind of nauseous at this point, fine, we came to a single integral now. But you might say, how did this help us? How did this Gauss's genius idea help us? Well, I'll say don't be sarcastic just as now. Still, the video isn't over, so I'm gonna introduce a quick substitution. Let u equal pi y. So we've integral half times sum from k equals 1 to infinity 1 over k squared. Upper and lower bounds unchanged. We have cosine of u over 2k plus y is u over pi, and dy is du over pi like this. And we can again take the LCM quickly over here. Integral from 0 to infinity, we'll have 2k pi plus u divided by pi. It will cancel out with this. So cosine of u divided by u plus 2k pi. Now we are going to use a really brilliant trick. What I'm going to do is, before writing anything, I'd like you to know that cosine of u plus 0 is equal to cosine of u. I mean that's basic, right? But how can an angle of 0 radians be represented? So if this is like the polar axis, you have 0 radians over here, and when you complete a complete rotation, you have 2 pi radians at the exact same angle, this point, and then when you complete another rotation, you have 4 pi at that. So you can represent this point over here as this angle rather as 2n pi, where n is an integral multiple, n is a positive integer, including 0, including 0. So I'm going to use this same strategy to write this is cosine of u plus 2k pi, because again k is an positive integer, and that was allowed over here, divided by u plus 2k pi du. And you are saying, why didn't we add and subtract? But the thing is, remember how cosine of u plus 0 was cosine of u. 0 we just represented using this 2n pi thing. Here n is k because that's our running index and that's the denominator, and it will be helpful later to do a helpful substitution. So this 2k pi is like adding a 0. It doesn't change anything. So, and how did that help us exactly? That's because we can introduce another substitution, because the denominator and the numerator are the same. So let w equal to u plus 2k pi. So dw is du, but although it doesn't change our differential factor, it significantly alters an upper or lower bounds. So for 0 we have 2k pi, and for infinity we'll still have infinity, and we have cosine of w over w dw. Okay, so now this integral over here is actually a special integral. It's a non-elementary special integral functions. So we call it the cosine integral function. We call it Ci of any argument x or w or anything. And I'm going to elaborate more on this on the next page. See you there. So the cosine integral function, call it Ci, cosine integral of say x for now, is defined as negative integral from x to infinity of cosine of t over t dt, where t is some dummy free parameter. And this has actually another form, which is Euler Mascheroni plus natural log of x plus integral from 0 to x of cosine of t minus 1 over t dt. And in our case, instead of starting from any other value, we are specifically starting at 2k pi, if you remember. But we don't have this negative sign, so multiply both sides by negative. So if negative Ci of 2k pi is defined as integral from 2k pi to infinity of cosine of t over t dt. This is exactly what we had to find. Instead of t, we had a w. So, and since t is anyways a free parameter variable, dummy variable, it doesn't matter. So we have to make that change here as well, if we're making everything into w. And multiplying both sides by negative, we'll have a negative Euler Mascheroni, negative natural log of x is 2k pi, so 2k pi, negative integral from 0 to 2k pi of cosine w minus 1 over w dw. And what I'm going to do is I'm going to plug this back where we, in place of this. And using recognizing our original integral as a cosine integral was helpful, because then that just enables us to refer to mathematical literature where uh, this stuff was found. So let's do that. Let's plug in and substitute. So back to the I naught page, we can write this as half times sum from k equals 1 to infinity of 1 over k squared with a minus Euler Mascheroni minus natural log of 2k pi we had a minus integral from 0 to 2k pi of cosine of w minus 1 over w dw. With a negative we can switch the order, so we'll have a plus then, integral from 0 to 2k pi of 1 minus cosine w over w dw. That's our plugged in value now. So and when we say split this up now, we have minus Euler Mascheroni over 2 times sum from k equals 1 to infinity of 1 over k squared. And then for this we can split this up into minus um, half times natural log of 2 sum from k equals 1 to infinity of 1 over k squared. Then minus 1 over 2 sum from k equals 1 to infinity of natural log of k over k squared minus natural log of pi over 2 sum from k equals 1 to infinity of 1 over k squared. And then this part basically we are just writing as it is, integral from 0 to 2k pi of 1 minus cosine w over w dw. All of this stuff basically simplifies to minus Euler Mascheroni pi squared over 12 minus natural log 2 pi squared over 12 minus half Riemann zeta prime of 2 minus natural log of pi squared over 12. And then, since we still had a sum running, I forgot to write the sum that was running, sum from k equals 1 to infinity of 1 over k squared, because we still have a k um, in the upper bound here. So it's sum running, then this integral. Forgot to put that in between here. So what I'm going to do is basically make a substitution, because this summing index is in the argument in the upper bound of this integral, and we don't like that. We want it in the argument in the integrand. So make a substitution. W equals 2k pi y. So we just have half, that was a half 2, sum from k equals 1 to infinity of 1 over k squared, integral now from 0 to 1, you can check that, 1 minus cosine of 2k pi y over 2k pi y, and then we have 2k pi y, 2k pi rather, along with her dy. So these cancel out, the 2k pi factors cancel out. So now we just have minus Euler-Mascheroni pi squared over 12 minus natural log of 2 pi squared over 12 minus half of Riemann zeta prime of 2 minus natural log of pi squared over 12, half of sum from k equals 1 to infinity of integral 1 over k squared, integral from 0 to 1 of 1 minus cosine of 2k pi y over a singular y dy. So what I'm going to do is I'm going to consider all of this together on a fresh page. See you there. Calling it S. S is defined as half times sum from k equals 1 to infinity of 1 over k squared, integral from 0 to 1 of 1 minus cosine 2k pi y divided by y dy. And trust me, don't waste your time calculating this integral. What you do is you assume uniform and absolute convergence. Interchange the sum and the integral. If we did it once to get this sum, we interchange the sum and integral because this was originally inside the integral. We can do it again, we can reverse it. So we have half times integral from 0 to 1 of, take the 1 over y outside, we have sum from k equals 1 to infinity of 1 over k squared minus sum from k equals 1 to infinity of cosine of 2k pi y over k squared, but still we have a dy. So we know this is the Riemann zeta of 2, which has a value of pi squared over 6, but we don't know this, so let's calculate this separately. So sum from k equals 1 to infinity of cosine of 2k pi y over k squared. So what I'm going to do is use the exponential definition of the cosine on this, half of sum from k equals 1 to infinity of e to the I times 2 pi y, entire thing to the kth power, over k squared, minus half sum from k equals 1 to infinity of e to the minus I 2 pi y, actually there's a plus, to the k over k squared. Notice this fits a form. This is nothing but the Dilogarithm of e to the I 2 pi y plus half of Dilogarithm of e to the negative I 2 pi y. And there is actually an identity for Dilogarithms we can use. So if you have the Dilogarithm of z plus the Dilogarithm of 1 over z, that is nothing but negative pi squared over 6 minus half of natural log squared of negative z. But take z in this case, in our case, to be e to the negative I 2 pi y. This, because if you write 1 over z, it's basically be the positive version, positive power, or this. So it fits the form. So take the half outside, apply this formula. We have negative pi squared over 6, negative half of natural log squared of negative e to the negative I 2 pi y. But natural log squared is natural log of the argument, the whole thing squared. So we can write as minus pi squared over 12 minus 1/4 of natural log of minus 1 plus natural log of e to the negative I 2 pi y, entire thing squared. So we have minus pi squared over 12. Natural log of I will be I pi because of e to the I pi being equal to negative 1, Euler's formula. So we have minus 1 over 4 I pi, this will be minus I 2 pi y, entire thing squared. So if you just take the square quietly, I pi squared is negative pi squared, and then we have plus 4 pi squared y minus 4 pi squared y squared. We have minus pi squared over 12 plus pi squared over 4. The others will cancel the 4 out, so minus pi squared y plus pi squared y squared. This simplifies to essentially pi squared over 6 minus pi squared y plus pi squared y squared. So this is basically what the cosine part turned out to be. So let's plug that in into our s. S is half of integral actually. Let me write that again. Half of integral from 0 to 1 of 1 over y. This first part turned out to be pi squared over 6, but we have a negative, the cosine part. So negative this pi squared over 6 plus pi squared y minus pi squared y squared dy. Nicely these two things cancel out. Half, then take the pi squared out, pi squared over 2, integral from 0 to 1. Then y's will cancel out, so we'll have 1 minus y dy. This turns out to be pi squared over 2. Then y minus y squared over 2, evaluated from 0 to 1. For 0 everything goes to 0. For 1 we have pi squared over 2 and 1 minus 1 squared over 2. So 1 minus half is half. So half and a half will make 4, 1/4. So pi squared over 4. That's what S turned out to be. Let's plug that back into our I naught. So ultimately I naught just turned out to be minus Euler Mascheroni pi squared over 12 minus natural log of 2 pi squared over 12 minus half of Riemann zeta prime of 2 minus natural log of pi times pi squared over 12, and this just turned out to be collectively pi squared over 4. That's I naught. Let's plug that back into our I2. So plugging it back into our I2 expression, we have natural log of pi times pi squared over 12, and then I naught was minus Euler Mascheroni pi squared over 12 minus natural log of 2 pi squared over 12 minus half of Riemann zeta prime of 2 minus natural log of pi times pi squared over 12 plus s, which was pi squared over 4. Notice these cancel out. I2 is just minus Euler Mascheroni pi squared over 12 minus natural log of 2 pi squared over 12 minus half of Riemann zeta prime of 2 plus pi squared over 4. That's I2. Let's go back and plug it into our general equation. And finally we are here at last, first page. I turned out to be I1, which is basically Euler Mascheroni times pi squared over 12 plus natural log of 2 times pi squared over 12 plus half of Riemann zeta prime of 2, And then this I2 that just turned out to be negative Euler-Mascheroni pi squared over 12 minus natural log of 2 pi squared over 12 minus half of Riemann zeta of 2 plus pi squared over 4. So these cancel out and they're all in order. All of these weird nasty expressions are cancelling out. And all we are left with I is basically pi squared over 4. Isn't that fabulous? Given all the troubles we took, it's just a simple answer. It's not, does not even involve like a Riemann zeta prime or any other weird special function. It has, known famous constants in it. Well, I actually know that this has actually been a really, really long video, but for old time's sake, which was integral from 0 to pi over 2, natural log of natural log squared of sine theta, divided by pi squared plus natural log squared sine theta, times natural log of cosine theta, divided by tangent theta, d theta. This was our I, which actually filled the space over here. Just turned out to be pi squared over 4, and we use this clever Gauss's genius idea of taking double integrals, and that works if you have natural log of 1 plus polynomial times natural log of 1 plus another polynomial. Then you can write one natural, a simple natural log as its Taylor series, and then somehow after integration by parts or any other minor process convert it into a double integral. So if you can't, any other methods are not working for you, because even for that I2 part, no Leibniz rule, no Laplace transform, nothing was actually working. We had to introduce a double integral. So I think you learned a lot in this video, and that's it. Let's stop here. So hey guys, please like, share and subscribe to my channel. Recommend me to your friends, your followers on Instagram, your fellow mathematicians, anybody. I don't care. I just want more subscribers. Like, let's keep a mark of 100 right now. And you can, in the meantime, you can basically follow me on Instagram, gamma underscore digamma. And meanwhile, while you are sitting at home in this crisis, have a great day. Peace out. Don't forget to love math and keep doing it. And don't lose hope, guys. Don't lose sanity. I know it's hard, but you guys will survive it. We shall overcome. So, finally, peace over and out.